So in our second part of section 7.5, we're going to continue working with conditional probability statements. So our next example says 2 cards are drawn without replacement from a well-shuffled deck of 52 playing cards. Part A is asking us simply, what's the probability that the first card drawn is a king? So the probability that the very first card is a king is simply going to be the 4 kings out of the 52 in the deck. Because they're only dictating what happens on the first card. The second card is not impacting any of our probabilities. It's just got to be a card. So that gives us 1 out of 13. Part B, however, is saying, what's the probability that the second card is a king, given that the first card was not the king? Okay, well, let's think about this from a tree point of view to see if that will help us some in terms of interpreting what's going on here. So this would be the first draw, or the first card. And it's either a king or it's not a king, so the complement. So we know that there are 4 kings out of the 52. And there are 39, 48 out of 52 that are not kings. Here we have another branching going on. This is our second card. And again, what we care about is whether it's a king or not a king. And specifically because we're looking at the second card being a king when the first one was not, I'm going to look at the bottom branching. I'm not going to bother to fill in the top one. I'm just trying to get a handle on my numbers. Okay, so if you have 1 card in your hand, we know that there are still 4 kings left in the deck out of 51. We know the not kings, we've got 1 not king in our hand. That means that there are 47 not kings left out of the 51. So because we're looking for the right side, given the left side, we already know that this has happened. Our answer is just going to be this number right here, the 4 out of 51. There are 4 cards left that are kings because we knew we didn't get a king the first time, and there are 51 cards that we're dealing with. So in terms of the formula, it really would be 48 over 52 times 4 over 51, all over 48 over 52. So here's the intersection divided by what has already occurred. These are just going to cancel. And we're left with 4 out of 51 as our answer. So again, I didn't draw the whole tree. I just drew enough of a tree to help me get a handle on what I needed as far as the numbers went, the probabilities. Let's try another one. So example 5. A pair of fair dice is rolled. What's the probability that the sum of the numbers falling uppermost is 5 if it is known that one of the numbers is a 3? So one number is a 3. Okay. Well, let's see if we can think about this from a slightly different point of view and not have to make a tree. So this right here is what is known. More importantly, it's what's impacting the size of the sample. So this is what reduces the sample space. So instead of having all 36 possible outcomes that fit this overall description, we're really just looking at the outcomes that have one number as a 3. So how many of those are that? Well, that would be the 3, 1, the 3, 2, the 3, 3, the 3, 4, the 3, 5, and the 3, 6. It would also be the 1, 3, the 2, 3, the 4, 3, the 5, 3, and the 6, 3. Notice I didn't list the 3, 3 again. The doubles are only listed once. So those are all of them that fit what is known. So instead of having 36 possibilities, I only have 11. So our denominator this time, instead of being 36, is just 11. And how many of these sum to 5? Well, the 2, 3 and the 3, 2 sum to 5. So that's 2 of them. So I didn't have to do the whole blown tree. I can make a much shorter route to my answer if I understand that this is reducing the size of that sample space from 36 to 11. And of those 11, here's that intersection. Of those 11, how many of them come out to be a sum of 5? And it's just 2 of them. So much shorter in terms of the process to get there, but the answer is 2 out of 11. Let's try another one using that approach. So this is example 6. For a 3-child family, find the probability of one girl given that the oldest or first child is a boy. And I'm going to write it as oldest because that implies the order that we need. So the oldest is a boy. Okay. So this is what's known. The oldest is a boy. So I'm going to come in and take a look at what those are. And I'm going to list them. So I could have boy, boy, boy. I could have boy, boy, girl. I could have boy, girl, boy. Girl, boy, boy would be the next one, but that doesn't fit because the oldest is not a boy. So I'm just going to scratch that off. Then I would have boy, girl, girl. I could have girl, boy, girl. Wait, that's no good. Girl, girl, boy. That's no good. And then all girls. So there's all 8 of them. But these 3 don't fit what we, these 4 don't fit what we know has already happened. There's only 4 of them that actually have the oldest child as a boy. Of those 4, which one have only 1 girl? Well, this one's got 1 girl and this one's got 1 girl. So 2 of the 4 have only 1 girl. So our answer is 1/2. So the probability of having only 1 girl, if you know the oldest child is a boy, is 1 out of 2. And that should make sense because if you already know the gender of the oldest child, there's only 2 children left in that 3-child family, and you only want 1 of those to be a girl. So it's going to be half of them, right?